right there, Chem Scholars. So, as I hinted at in the last video, the next conversation is going to be about energy, a couple of different forms, and one specific type of energy that we can talk about from the periodic table point of view. So, energy is one of those very generalized terms that we can use a lot, but not necessarily define very well. Okay? The physics definition says energy is the ability to do work, the exertion of force to overcome friction or molecular change. Yeah, that's not too helpful, really. Okay, think of it this way: energy is what allows things to happen. Okay, if you didn't have energy, you could not get up, you could not talk, you could not breathe. Okay, everything has energy, whether it's a low amount or not. Okay, a rock on the ground has some amount of energy because it has some temperature, so it's got to have some molecular motion and so on. Okay, there is a law of thermodynamics that basically says you can never not have energy, but again, we're not really going to get into that idea. Okay, so important thing to understand is in the metric system we use a unit called the joule, named after James Joule, in case you care. The symbol for it is a capital J. Okay? There are many different forms of energy. They're all going to be measured in joules, although very often we will see kilojoules, just because we're dealing with such large quantities. A joule is actually a pretty small unit. Okay, if you were trying to take a cup of water, and let's say this cup of water is, just an ordinary drinking glass, 8-ounce cup, okay, and you were trying to heat that up by just 1 degree. So let's say it came out of the tap at 19 degrees Celsius. You want to make it 20 degrees Celsius, okay? It would take almost 1,000 joules of energy to just bring that up 1 degree, okay? So we're talking about a very small unit, okay? But don't worry about it more than that, okay? There used to be something called the calorie that was used, that was created for the metric system. And then the food industry came along and changed it to capital C calorie because they wanted to use it, but at the same point, the calories were also small, so they wanted a bigger unit, so their unit's a little bit bigger. So really, one capital C calorie is 1,000 little c calories. But again, that's food industry stuff. That's not us. Okay? Like I said, there are many different forms of energy, but predominantly we talk about two main classes: kinetic, potential. Okay, kinetic energy is energy of motion. Okay, so in chemistry, I said a little while ago that molecules and atoms are always in motion. So kinetic energy is very, very common that we talk about. And one of the most common ways is something called thermal energy, which again is the kinetic energy of the atoms and molecules as they're moving. Okay, you'll see some of the other forms, and we might talk about mechanical energy at some point and so on, but not too much. Okay. On the other side, we have potential, and that's stored energy. Okay, well, energy can be stored in many, many different ways, and electrical energy does relate to stored energy, and since we're dealing with electrical charges and whatnot, it factors in significantly. So when bonds are made and something called intermolecular forces are made, energy is stored in those bonds, and if a bond is broken, we release the energy. Okay, likewise, nuclear energy does the same thing, but holding the energy in the nucleus. Okay, we talked about the idea that neutrons are the glue holding those protons together, right? But protons are positively charged. They repel one another. They don't really want to be in there. So if we hit that thing just right, bang, we break it open and release a whole lot of energy. Okay, so in any event, they are stored energies that we're talking about. Okay. Now, relating to that is a form of energy that is referred to as heat, but it's really not a form of energy. Okay? Heat is a process of transferring energy from an object with a lot of thermal energy to an object with lower thermal energy. Okay? So heat is a change in energy. It is a transfer of energy. Okay? So we have to keep that in mind. But again, it does relate to energy, so it's still measured in joules, or again, more specifically, kilojoules. Okay? And I always like to emphasize the difference. People say heat is how much temperature something has. No. Okay, temperature relates to thermal energy. Okay, temperature is just an estimation of how much thermal energy it is. Okay, before we were able to actually measure thermal energy, we had these things called thermometers that would give us an estimation of temperature. So it roughly was saying how much motion something had. Okay, heat is about a change in energy. Okay, so if there's heat involved, that means the temperature has to be either going up or down. Something's got to be giving off energy, something's got to be accepting energy. So temperature and heat, not really related in that way. Okay, so please keep that in mind. Okay, in terms of transferring thermal energy or heating something, there are three ways: conduction, convection, radiation. Okay, conduction means direct contact. Okay, so you have a pot on the stove, you put your hand on it, ow! Well, you just conducted heat to your skin. Okay, you got that pot of water on there, and you put your hand over it, and you can feel the steam coming up. You can feel heat. That's convection. Okay, convection is transfer of heat through the motion of a fluid. Okay, so that's liquids and gases that are moving and helping them bring the heat around and transfer it. So you know that hot air rises, cold air sinks. Okay, so if we had a Bunsen burner going, the Bunsen burner is going to heat the air right above it, causing it to rise, causing cold air to come down and get heated and rise, and then we get this circulation going where hot and cold air start movement. That is convection. If you have a convection oven, basically they put a fan in front of some heating elements to help circulate the heat, to get the air inside the oven moving, to help speed up the cooking process, because conduction is only able to do so much. Okay, the part of the food that's touching the pan is limited, and you want the whole thing to cook. And yes, part of the way oven works is also by something called radiation. Okay, radiation is transfer of energy by subatomic particles moving in waves of wave-like patterns. Okay, we give off radiation. Okay, if you've ever seen people in infrared goggles, they put them on and they can see reds and yellows and greens on people. Okay, that's because we give off infrared radiation. Okay, if we don't give off radiation, we got a problem. Okay, ovens do radiate too. Okay, some people's houses have baseboard radiators and whatnot. They're radiators, they radiate energy. Okay, so going back to the pot on the stove, okay, we said if you touch it, that's conduction. If you put your hand over it and you feel the heat, that's convection. Well, if you put your hand alongside of it, okay, you feel heat coming off of it. That's because it's radiating heat. Okay, now radiation is distributed in all three dimensions, really, so even your hand above it technically is getting some of that. But if you put your hand alongside of it, you would not be getting convection, and you're definitely not getting conduction. Okay, so any heat you feel that way has to be radiation. Okay, all right, now heat is going to be something we come back to later in the unit, but we're going to talk briefly about one other type of energy specific to atoms called ionization energy. Okay, you see the word ion in there. An ion is a charged particle. Okay, so that means that in ionization we're talking about changing the charge of something. Well, specifically it's defined as the minimum amount of energy required to remove an electron from the ground state of an isolated gaseous atom or ion. Okay, really wordy. Don't worry about the ground state part because we're not ready to explain that. What we're saying though is that technically when they measure ionization energy, they make sure that the element is in its gas state. So even an element like lead, which is pretty dense solid, okay, they vaporize it and then check the ionization energy. So it's always in gas form, and that's why at the bottom of the page you see these little G's in parentheses that's just saying gas. Okay, so we're just again emphasizing that it's only done as gases. Okay, even though elements aren't gases at room temperature, well, we can change the temperature, we can make them gases. Okay, there are multiple ways of going about that. Okay, so it's energy needed to remove an electron from the atom, simplified down. Okay, so we're talking about putting some form of energy in, possibly heat, maybe electricity. Okay, we're putting some form of energy in order to rip the electron away. Remember, the electrons are being attracted by the protons in the nucleus, right? So as that attraction is there, it takes energy to break an attraction. You're going against what's going on there, so it requires energy. Okay, so energy has to go in to get the electron out. And that's what, again, this equation is saying that, you know, if I take an atom and I throw in energy, which maybe I should have, you know, put plus energy, Okay. Then we get a sodium ion and an electron out of it. And it says specifically that the amount of energy is 496 kilojoules per mole. Well, we don't know what moles are. We talked briefly about kilojoules. So for now, just think of it as 496 units of energy. Okay, let's not even worry about anything more than that. So that's the idea of ionization energy. Okay, why are we talking about ionization energy? Well, two reasons. One, we have to talk about ions at some point, and two, we're talking about the periodic table. So let's keep that in mind. Okay. Now I use the term first ionization because, well, atoms have very often more than one electron, and we could take more than one electron away. So there's a certain amount of energy to take the first electron away, but once you take the first electron away, now there are less electrons, right? So there's less repulsion, so the atom's going to get a little bit smaller, and that's going to mean that it's going to be harder to pull the next electron. So as we look at this equation down here, now that we already made the sodium ion in the first step, now we're taking another electron away, so now we're making it a 2+ ion. And yes, sodium doesn't want to be a 2+ ion, but that's a separate issue. When we take that electron away, now, before it took 496 units of energy, now it's 4,560 units of energy. It's a significant increase. Okay? Why does the first electron come from sodium so much easier than the second? Well, again, two reasons really. First off is the fact that whenever you take an electron, the size of an atom is going to get smaller, which is going to make it more difficult. But if I can backtrack real quick here. Where am I? There. Okay. You notice that sodium has one valence electron, right? Out here, it has one valence electron. So when I take that first one, it's further away from the nucleus. When I go to take the next one, now I have to go closer to the nucleus. So it's going to be even harder because electrically speaking, we just got closer to the protons, which are holding harder. Okay. So whenever you jump between energy levels like that, you're going to see that the ionization energy goes up dramatically. Okay. All right. So let me come back down there. I could have done that. All right. No, that's where I want to be. So let's talk about this idea. So we're going to talk about element in the third period. So we were talking about the third period before: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay. So we're talking about some element in that row. The first electron requires 787 units of energy to come off. The second one requires 1575 units of energy. The next one requires 3220 units of energy. The next one requires 4350 units of energy. The next one requires 16,100 units of energy. Okay? From that information, we should be able to identify the element. And the logic goes to what we were talking about a moment ago. I said when you jump between energy levels, you're going to see a tremendous jump, a significant jump in the amount of energy. Where is that significant jump? Well, the first four, we see a pretty steady progression, and then the fifth one is way more energy than these are, right? I mean, this one is more energy than all the others combined. So clearly the fifth one is a different energy level than the other four. That means that this element must have 1, 2, 3, 4 valence electrons. And so if I look at the fourth row and I look for 4 valence electrons, I know that I have to be talking about silicon. Okay? So there's the logic to that. And again, something we should be able to look at a periodic table and kind of interpret some information. Okay? Now, let's go back to talking about it from the periodic table as well, a little bit more. We said, oh no, we did not say. It is easier to remove a valence electron from a bigger element than a smaller one. Why would that be? Okay, well, again, with the valence electrons in a smaller atom, that means they're closer to the nucleus. Distance matters, okay? So the smaller the distance, the stronger the attraction. So smaller atoms tend to hold their electrons more tightly, and so it would take more energy to remove an electron from a smaller one, okay? So with that in mind, let's compare those elements. We said sodium to magnesium to aluminum, silicon, phosphorus, sulfur, chlorine, argon. The size decreases from left to right. Well, if it's getting smaller, and we just said that smaller atoms have bigger attractions and so are going to require more energy, that means the ionization energy has to increase. Okay, so we have an opposite trend. Okay, sodium is the biggest one. It's going to be the easiest in the third row, the third period, to take an electron from. Argon is the smallest, the happiest one there. It's going to be very hard to take an electron from. Okay, so ionization energy increases from left to right. Okay, what about from top to bottom? Well, we said that the size increases as you go down, right? Helium is the smallest, then neon, argon, krypton, xenon, radon, organoson. Okay, so if it's getting bigger as you go down, then it should be getting easier to take an electron. And so ionization energy decreases from top to bottom. Okay, so again, those two trends we've talked about are the exact opposite. Okay, from left to right, we said the size decreases, well, that means the ionization energy increases. And we said from top to bottom, the size increases, so that would mean the ionization energy would decrease going down. This arrow showing it's increasing going up. Okay, so two different trends that you need to keep in mind. Okay, that's where we're going to stop for now. Talk to you soon.